So this is going to be the lecture over chapter 10. And what we're attempting to do here is to figure out a way in order to be able to make dose computations within a phantom. We've discussed up to this point methods, one method in order to be able to do that, the percent depth dose. The problem that we run into there is that it's dependent upon SSD, and what we'd like to be able to do is to get away from that. If you'll remember from chapter 9, one way that we tried to get away from doing that was to use the tissue to air ratio, in which it was SSD independent. It didn't matter where it was. We were trying to figure out a way in order to measure dose in free space and compare that to a dose measured in the patient at a particular depth. And by doing that particular ratio, we could free ourselves from having to measure the source to skin distance. And the problem with doing that, as this paragraph here, the key points of chapter 10 points out, is that it's okay to do that for the low energy beams up to about Cobalt 60. But by the time you start getting into the higher energy beams, the ability to be able to measure dose in free space becomes problematic. You have to have larger and larger buildup regions, and it becomes more and more difficult to be able to come up with a dependable measurement there. Therefore, we go ahead and try to develop other methods by which we can do that. So that's the main point of this particular chapter. Is how do we go about doing that? What are our methods? So let's go back here to the beginning of the chapter. Okay, so now we've got a concept of the tissue phantom ratio that will help us overcome the limitations of the TAR. And this quantity relates the properties, or retains the properties, of the TAR, but limits the measurements to the phantom rather than in the air. So in other words, we no longer have to take a measurement in air in order to be able to make this kind of system work. And then a few years later after that, we've got Holt, that's just introducing yet another quantity called the tissue maximum ratio, which again confines the measurements within the phantom, so you don't have to worry about what's going on in free space. So what we're going to do is we're going to take the dose at some point in the phantom, and we're going to break it into two different components. We're going to have a primary component, and we're going to have a scatter component. The primary dose is contributed by the primary or original photons emitted from the source, and the scattered dose is going to be the result of the scattered photons. The scattered dose also gets split into different components. They're going to be collimator as well as phantom components, because what goes on in the phantom can be determined independently of what goes on with the collimator. So in other words, blocking a portion of the field doesn't significantly change the incident output or photon energy fluence in an open portion of the beam, but it might significantly reduce the phantom scatter depending on how much blocking you're doing. So because of that, we're going to take these different components, the primary and the scatter, and we're also going to take the scatter and start breaking it up into different components. Now we have one practical difficulty, the determination of primary dose in a phantom that excludes both collimator and phantom scatter. For megavoltage beams, one may, as a reasonable approximation, consider collimator scatter as part of the primary beam. so that the phantom scatter could be calculated separately. So we're going to define an effective primary dose as the dose due to the primary photons, as well as those from the scattered, as well as those scattered from the collimating system. The effective primary in a phantom may be thought of as the dose at depth minus the phantom scatter. So alternatively, the effective primary dose may be defined as the dose expected in the field when scattering volume is reduced to 0 while keeping the collimator opening constant. There's some discussion here about being able to find the primary dose in a 0 by 0 field. What we're going to do is say that the primary dose in the phantom is usually represented by the dose of a hypothetical 0 by 0 field, which is obtained by extrapolation of the depth dose versus field size data. Okay, so the beam output measured in air depends on the field size. As the field size is increased, the output increases because of the increased collimator scatter, which is added to the primary beam. So the collimator scatter is also called the in-air output ratio and may be defined as the ratio of the output in air for a given field to that for a reference field. So the collimator scatter, S sub C is how it's usually reflected, may be measured with an ion chamber with a buildup cap. The measurement setup shown in figure 10.1.A. Ionization readings are plotted against field size and the values are normalized to the reference field. Offhand, I'm not seeing. There we go. So we've got our buildup cap, we've got the reference field, we've got SAD, and we're going through and we're measuring it, and we're taking the S sub C factor, comparing it to a reference field. That's how we're measuring it, or making our reference field. And then the other fields are going to be in relation to that, so that the factor here can be somewhat below 1, it can be above 1, so on and so forth. So in the measurement of S sub C, the field must fully cover the buildup cap for all field sizes if the measurements are to reflect relative photon energy fluences. A lateral margin of at least 1 cm between the field edge and the buildup cap is considered to be adequate. So for high energy photon beams, the required buildup cap size can become too large to be able to measure that for small field sizes. For these cases, Van Gasteren proposed the use of a narrow cylindrical beam coaxial phantom or mini phantom with a measurement depth sufficiently beyond Dmax to avoid contamination electrons. So we'll look at the mini phantom here coming up in figure 10.2. So normally the collimator scatter factors are measured with the chamber at the source to axis distance. For small fields, one may take the output measurements, including those for the reference field, at distances larger than SAD, so that the smallest field covers the buildup cap or mini phantom with suitable margin. So that's the collimator scatter. The phantom scatter takes into account the change in scatter radiation originating in the phantom at the reference depth as the field size is changed. SOP may be defined as the ratio of the dose rate or dose per monitor unit for a given field at a reference depth to the dose rate. So here again, referencing this chamber with buildup cap in air to measure relative output data for determining S sub C, and then measuring in a phantom at a fixed reference depth for determining S sub CP versus the field size. So source to SAD is source to axis distance. So you can see that here in both cases. You can see the reference field here, and you can also see the field that's being measured, which is the dashed line. So they're making a comparison here between what we're seeing in air and what we're seeing in phantom. So we can go through and find more information about this. This is more than what I would really prefer to go into. However, this does lead us into the TPRs, which is eventually going to get us to TMRs, which is the big thing that is being used for measurements nowadays. And that's what physicists seem to gravitate towards. TPR is defined as a ratio of the dose at a given depth in a phantom to the dose rate at the same source point distance, but at a reference depth. So let's take a look at figure 10.3 to kind of see what we're talking about. So we've got a depth that we are interested in, and then we've got a reference depth here. If the reference depth happens to be the maximum dose, then the tissue to phantom ratio becomes a tissue maximum ratio. And so the TMR is considered to be a special case of the TPR. So the corresponding quantity for the scattered dose calculation is called the scatter phantom ratio. I've never seen that really used in much of our calculations. So the reference depth of maximum dose as determined above should be kept the same for all field sizes and all the relevant dosimetric quantities. So for the TPRs, we denote the reference depth by d sub naught. If d sub naught is chosen to be 10 cm, the formalism for the dose calculations based on TPRs must also ensure that all the relevant dosimetric quantities are normalized to the same reference depth. All right, so for TMRs, tissue maximum ratios, it is assumed that the fractional scatter contribution to the depth dose at a point is independent of the divergence of the beam and depends only on the field size at the point and the depth of the overlying tissue. It has been basically shown to be true, so we go with it. This principle, which also underlies TARs and TPRs, makes all these functions practically independent of SSD. So a single table of TMRs can be used for all SSDs for each radiation quality. Obviously, you can see the definition here of TMR, and you can see how TMR and percent depth dose are interrelated by the following equation. You can see here that F is going to be the SSD, the reference field size is going to be adjusted for the depth here. And you can see that R for D naught is also, or for T naught is also adjusted here at the reference depth as well. These are field sizes that are adjusted depending on where you are, how deep you are in the phantom. TMRs can be measured directly, but they can also be calculated from percent depth dose. And then they can be used to calculate from that, you can get the TMRs. They can also be derived from TAR data, such as from Cobalt 60. And if you take equation 10.4 and generalize it to TPR, then it ends up becoming this. So let's take a look here at calculation of monitor units, because all of us talk regarding TMRs, TPRs, and PDDs and whatnot. It's got to lead somewhere, and where is it going? Well, in order for us to be able to use this information, what we're going to do is we're going to figure out basically how long do we leave the machine clicking. And that's what we're going to be looking at here. So the radiotherapy institutions vary in their treatment techniques and calibration practices. Machine calibrations are carried out in a water phantom at a reference depth, the standard SSD, or at isocenter. Although most institutions currently use a reference depth of maximum dose, some prefer 10 cm depth as a reference depth. In addition, clinical fields, although basically rectangular or square, are more often than not shaped to protect critical or normal regions of the body. So we need some sort of calculation system in order to be able to tie those concepts in to deciding how long the machine needs to be on. And these are the general equations that you guys will need to know. For isocentric fields, MUs are going to be the prescription dose, and then divided by several other factors. The factors here, you've got your calibration factor, you've got your collimator scatter, you got your phantom scatter, TPR, any sort of wedge factor. You've got OAR. You basically have your inverse square law adjustment here. You have the tray factor here. I think I skipped over that. Yeah, the factor over here, you're looking at source to calibration point distance and source to point of interest distance in which D is delivered. Essentially, you're looking at adjusting a little bit there for the certain distance away from the source, those corrections. You have different computations here for isocentric fields, and then for non-isocentric fields, you're seeing some adjustments here. You're noticing that the TPR and the TMR are being replaced with the PDDs, and you can also see some adjustment here to some of those factors as well. Now, all of this is pretty well spelled out here in as far as what all of these terms mean. The calibration dose per MU is specified at the source calibration point distance, SCD, source calibration point distance, for the reference field size and the reference depth. Now, in many of these cases, we will go through and we'll come up with certain problems here about how to use these particular monitor unit formulas. Most of the time, when you're looking at a chart or you're checking to see if you're going to, go into a chart to start a particular patient, you're not going to go through the computations like this. But this is sort of what's going on in the background. So let's take a look here at example 1. So you've got a 4 MV linear accelerator and 4 MV energy, and it's calibrated to give 1 centigray per monitor unit in the water phantom at a reference depth of maximum dose of 1 cm. You've got 100 cm SSD, a 10 by 10 field size. So we're going to determine MU values to deliver 200 centigray to a patient at a 100 SSD 10 cm depth at 15 by 15 field size, given all of these other factors. So if you go through and if you plug in using equation 10.14. In other words, this one, it's considered to be non-isocentric simply because at 100 SSD, for most machines, that isocenter would be right there on the skin. So we're going to use equation 10.14, which is for non-isocentric fields. So the dose calibration term here, or let me start off with the dose here on the top. Dose that we want to deliver is going to be 200 centigrade, so we put that here. This decal calibration factor, we're delivering 1 centigrade per MU, so we put that here. We've got the collimator scatter, which is going to be this. We have the phantom scatter, which is going to go here. 0.651, this is going to be our percent depth dose. We change that to a decimal, 0.651. And we put that in here. There is no wedge factor or tray factor here, as we have not been given a wedge or a tray to insert. So both of those are going to be 1, because we don't make them 0, we make them 1, because what we're saying here is that the dose rate is not being changed by those two elements. So our default position to put that in is going to be 1. And then finally, we're looking at the OAR as well as source calibration distance divided by the SSD plus T0, which in this particular case, this ends up being just 1. So when we go through and we multiply all of that together at the bottom, we get a result. So it's going to be 200 divided by some number that's, considerably less than 1, and it turns out to be 298. Normally, you're not going to end up filling this in on sheets like this. But in order for it to go through and to make the calculations, it used to be that you would fill it in sheets like this, but not so much anymore. So here's an example using, again, 10.14. We're going to determine the MUs for the treatment conditions, given example 1 above, except that the treatment is SSD is 120. And we have the collimator scatter factor change, and the percent depth dose is now going to be 66.7. So with all of that, the field size projection at SAD, or at 100, since we're delivering it at 120, and that's going to be our field size for the collimator scatter factor at that point. It turns out that at SAD, this turns out to be 12.5 cm. So we know what the collimator scatter factor is there. We know what the phantom scatter is going to be at the distance we're treating, 15 by 15. The SSD factor is going to be the source to calibration factor, which is 100 plus 1. Divided by the new SSD, which is going to be 120 plus 1. So that ends up being 0.697. So we plug in these corrected factors here. So we know what the new PDD is here, and we also know what the new SSD factor is. And we come up with 422. This is much greater than what we had calculated here at 100, at 298. That stands to reason. For example 3, we're looking at a tumor dose rate again of 200 is to be delivered at the isocenter, which is located at a depth of 8 cm, given a 4 MV X-ray beam. Field size of the isocenter is 6 by 6. The scatter factor, the collimator scatter factor is 6 by 6 is going to be 0.97. Phantom is going to be 0.99. Machine calibrated at SCD of 100 and TMR. Putting all of that into equation 10.13, since we know what the TMR is, we can put that information in, and that corresponds to equation 10.13. We're putting in all of the basic factors here that we know of in, and we're coming up with 265. Again, if we take this and decide that we're going to use the unit calibrated non-isocentrically, not many of these factors are going to change except for this. So a lot of the same process for Cobalt units is going to be pretty much the same as what we just went over. But for Cobalt units, we're going to be looking at time. How much time do we leave the shutter open, as it were? So in order to do that, we're going to use the same basic equation, except we're going to change around. Rather than have number of monitor units here, we're going to have time, and rather than just have 1 centigrade per monitor unit, we're going to change this to time, which is going to be in this particular case the dose rate under the calibration conditions. So for this particular problem, we've got a tumor dose of 200 centigrade. It's going to be delivered at 8 cm depth using a 15 by 15 field size at 100 SSD, and the penumbra trimmers up. The unit is calibrated to give 130 centigrade per minute in phantom at a 0.5 cm depth for a 10 by 10 field with trimmers up, and SSD is equal to 80. Determine the time of irradiation given the collimator scatter factor, the phantom scatter, and the PDD. So in order to be able to do that, we need to figure out at SAD, pardon me, since this is a Cobalt unit, we're looking at 80 centimeters. We need to be able to take the 15 by 15 here and try to figure out what that is at this particular SSD. We share it down, since the SSD we're interested in is 80, and normally this unit is calibrated, or it looks like it's at no, we know what the field size is at 100. We need to know what it is at 80, where it is calibrated, sorry. So in order to do that, we come up with 12 by 12. When we use equation 10.14, when applied to Cobalt therapy, we plug in the values that we know. This primarily being 130 centigrade per minute is now a dose rate, as opposed to just dose per monitor unit. The rest of these factors we can kind of fill in. This is the only one that you may not be familiar with. F in this particular case is 100. The calibration of the maximum distance is 0.5, so we can put that in here. And the SCD is going to be 80.5 because the unit is calibrated at 80 SSD, and the maximum is 0.5 cm below the surface. Putting all of that in, we come up with 3.4 minutes. Generally, when we're looking at monitor unit calculations, we're not looking for how many minutes something is on. We're looking for how many monitor units will be dispensed. Okay. We will have some discussion here regarding regular fields and how to go about computing those. We'll also need to talk about points off axis, where it's possible to calculate depth dose distributions at any point within the field or outside the field using, we can do it using the Clarkson technique, but it's not practical for manual calculations. So if we want to be able to do that, we need to be able to come up with something called an off-axis factor. So the off-axis factor in this particular case, we're looking at situations such as what you see here, where you have examples of irregularly shaped fields and equivalent rectangles for dose points. For dose at points of interest are shown by the dashed lines. Points versus equivalent rectangles are A, G, H, K, I. So from here to here. Oh. Okay, that's a weird way to write that. Okay, the point of all of this here is for you to be able to do a calculation, even though, let's say that your on-axis point or central axis is blocked for some reason. It's not, again, Clarkson's method is not good for practical calculations in this case. So let's say to calculate dose at any point Q, the field is imagined to be divided into 4 different sections, such as in figure 10.10, like this, where you have central axis here, but you're interested in a point here. So what we're going to do is we're going to take this particular field and we're going to cut it up, and we're going to cut it up into 4 different shapes. And the contribution is going to be computed separately. So the dose at depth D along the axis through Q is given by 1/4 sum of the central axis dose at depth D for these two, for the fields this, 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 and this. So suppose the dose in free space on the central axis through P at SSD plus D sub M is 100 centigrade, and its value at a corresponding point over Q is this, where K sub Q is the off-axis ratio determined in air from the primary beam profile. If the backscatter factor and central axis for rectangular fields are obtained, the dose at depth D along the axis will be given by this. So we're going to take the K sub Q, the off-axis ratio, multiply by 100, divide by 4 for the sum of the backscatter factor times the percent depth dose at depth D for each of these 4 fields. Those 4 fields. Since the D max at P is 100 times all of this, then the percent depth dose at depth D along the axis relative to this will be given by all of that. I'm going to see if I can give you a little bit of a better off-axis description than what is being written here, something that's a little bit more straightforward. But we do have a computation here where let's suppose in figure 10.10, something like this, that the overall field size is 15 by 15. Find the percent depth dose at point Q at 10 cm depth, given all of these dimensions for A, B, C, and D. Assume a Cobalt 60 beam with K sub Q of this and SSD of this. Using that above procedure, the the required percent depth dose is going to be given by 4 times a backscatter factor of 15 by 15, since that's the sum of each of the sides. And then we go through and we compute what all of these different field sizes are, and then multiply it by the percent depth dose that corresponds to that. Which is just whole bunches of fun. So let's see. There's Day's method. I have not seen Day's method on that is discussed in any of the questions so far that I see for the registry, but I will see what might exist out there regarding Day's method and see if it's something that you need to know. You're welcome to look through that material there, but I'll find out exactly how much time we need to put onto that. For right now, I'm going to leave it at that, and I'm going to go through and see exactly what types of problems we need to work, and we will find out here very shortly. And I will work problems, have problems available for you, and do lecture over those said problems as well.